This is lesson 14. We will use it to develop our growth idea further. When you invest money, you don't sit back and watch it doubling, but you do watch it grow slowly. Refer to how it grows in terms of its interest rate. If it grows by 20% every year, we use 1.2 as the multiplier. Now it's worth investigating this multiplier a little bit further. The 1 represents the original amount and the 0.2 is our way of indicating 20% extra. So if it grows by 20% every year, we have 20% more than we started with, so we have the original and the extra 20%. So we express percentage changes in terms of a multiplier. So for type 1, we have the original value is allowed to change a number of times by being multiplied. So we're able to get a new value. Assuming we invest $1 at 20% for a few years, we have the following. After 1 year, the original has been multiplied once. It's $1.20. After 2 years, it's been multiplied twice. That gives us $1.44. After 3 years, it's been multiplied sufficiently to get us up to $1.73. And after 4 years, $2.07. So what we've got there is a 20% growth sees the amount double approximately every 4 years. Note that the general structure of this calculation is the original value multiplied by something a number of times. Or more compactly, new value, original value by the multiplier used repeatedly. And for type 2, we have these possibilities. Starting with the $1, letting it grow by 20% for 10 years would give us $6.2. Notice I've omitted the dollar sign in the calculations, but when I interpret this as an answer, I have to state what its units are. Now, another possibility, I have $1, I let it grow for a number of years until it gets to $10. How many years or how many times did it grow? Now, in this case, the unknown is not by itself. I've got to use an inverse of the growth process to go backwards. So we have now calculated the value that was missing from the original equation is 12.6. That means the $1 grew for 12.6 years to bring the amount up to $10 in value. Now this would be done on a calculator, and the calculator's instruction manual would tell you how to do it. We'll look at that in more detail later, but for the moment all we want to know is that if it increases by 20% 10 times, we get to $6. But if we let it grow for 12.6 years, we get to $10. Remember, the numbers have relevance. If the original one was $1, the result of our calculation, $6.2 is what the original dollar is worth after 10 years. And the 12.6 is the number of years the investment was left to grow until it became $10. The matching type 3 situation uses a graph to illustrate what we have seen. So, 10 years got us to $6.20. And the earlier examples are represented by a point on the graph, and the $1 starting point, we refer to that as the intercept. The vertical intercept represents the starting value. So a few points allows us to draw the graph. In each case, we choose an input and allow it to generate an output. Putting those together gives the diagram. Notice that in this case, we get a curve, and the points have been simplified slightly to make the curve easier to draw. Remember that this curve has a characteristic shape. It's referred to as an exponential graph. And for an exponential graph, we keep a focus on the point where it begins on the vertical axis, because that is the starting value. Now, if you divide the values of two consecutive points on the curve, you can calculate the multiplier. So if we go back to the graph, divide this output value by this output value, you will get the multiplier, 1.2. Now, for a moment, we'll look at the social relevance of this. Nobody's going to be offered an investment which grows at 20%. But poor people who are getting desperate are frequently offered loans at 20% or more. A debt for the person is an investment for the loan company. The most frequent result is it grows too fast for the person to repay, with devastating consequences for them. In some places, everything they own is confiscated and they are thrown into prison to effectively work as slaves. High interest rates have social consequences. Try this again with a 10% interest rate. The multiplier is 1.1. Now, if you look at the graph, you will find that the amount doubles in approximately 7 years. For some people, when the interest rate on a debt is 10%, it also reveals a potential disaster if they're not careful. When it is relevant in a financial situation, exponential growth is more commonly referred to as compound interest. Now, that was a short lesson which extended the previous one into a practical context. New words such as compound interest. But it's just simply what we did in the previous lesson, moved into the real world. We'll go on from there next lesson. I'll see you then.